clocks obey the rules of relativity. Naturally, these rules apply to the human clock. With a time-keeping device called metabolism, it starts running even before the moment of birth. And in a relatively predictable fashion, it keeps running to the end. But what would happen if the human clock were moving at nearly the speed of light? To find out, consider these identical twins, Albert and Henry. From the very outset, their biological clocks start out in perfect synchronization. Soon enough, however, the best laid plans of mother and father alike get out of sync. Instead of an orthodontist, Albert becomes a scientist. Henry chooses what's left of the wide open spaces, open space itself. Especially for identical twins, the first parting is such sweet sorrow. Nonetheless, traveling at nearly the speed of light, Henry has no trouble leaving Albert behind. This is Henry's first long haul for his new boss, the Interstellar Baking Company. Destination, Zog, 10 light years away. Assignment, take a load of ordinary white bread and exchange it for Zoggy cakes, those delicious little buns that all the earthlings crave. But that's not what's so extraordinary. If Henry could compare his clock to Albert's clock, he would find Albert's clock running slow. And if Albert could compare his clock to Henry's, he would find Henry's clock running slow. And that spells paradox. How can each one be slower than the other? Fortunately, in the theory of relativity, there's no problem at all. For one thing, there won't really be a problem as long as the two of them are far apart. But what will happen when they're not far apart? Say, when they get back together for a family reunion. Again, in the theory of relativity, that's no problem. Brother Henry, at nearly the speed of light, will take about 10 years to reach Zog, 10 light years away. And then another decade to haul his buns back to Earth. To Albert, that's around 20 years. But to Henry, the twin who's actually en route, the situation seems different. Since it's Lorenz contracted, the distance to Zog seems like a milk run. A few hands of solitaire, 40 winks, and as far as Henry's concerned, it's hello to the bright lights of Zog City. Then, equally quick, because the distance is again Lorenz contracted, it's back to Earth just as fast. And so, when they do get to compare those biological clocks, while the result is amazing, there's no paradox at all. Henry, the twin who zoomed away and then came back, has only aged a couple of months. But Albert, the twin who never switched inertial frames, has aged 20 years. And so, even among relatives, time is relative.
Try to imagine, if you can, a completely empty universe, a universe with nothing whatsoever in it. In such a universe, it would make no sense at all to speak of time or space. The very concepts would be meaningless. If there were one single object in the universe, it would still be true. Time and space would have no meaning at all. If there were two objects, then you could imagine saying, well, they're getting closer together or they're getting further apart. And then you're saying something about the flow of time and distances. If there were many, many objects in your universe, you might imagine using some of them to construct a device that could measure the flow of time or measure the distance between objects. But it would still make no sense at all in that universe to say one of these objects is at rest and only everything else is in motion. In such a universe, the simplest law of motion it would be possible to imagine is to say that each body continues in whatever state of motion it has until something interferes with it. And that, of course, is precisely the law of inertia. But that has to keep on making sense in a universe in which light can propagate through the void. Now, if light has some definite speed as observed from a particular frame of reference, then there is such a thing as a state of rest in that frame of reference. And the whole argument for the law of inertia collapses. Now, I don't know if there are any other logically consistent universes. But in our universe, that problem has been solved by making the speed of light the same to all observers, regardless of their state of motion. Knowing that, and only that, it's possible to deduce that if there are a pair of twins, and one of them stays behind on Earth, and the other one travels at high speed to a distant star, turns around and comes back, the traveling twin, when they get back together, will be younger than the one who stayed behind. I don't need to know anything about how clocks work, about quartz crystal oscillators, about human metabolism. All of those things are completely irrelevant. All I need to know is the principle of relativity and the constancy of the speed of light. And from that, I can deduce that the traveling twin will come back younger than the twin that was left behind. That is an absolutely breathtaking feat of pure human logic. That is the theory of relativity, and we'll get on with it next time.